Before we go any further in our visual algebra galore, I want to take a little time to talk about number representations, how we represent numbers and how this naturally merges from the way we did visual calculations in visual algebra. So you might, for example, remember the copying machine that represented 1/3, that is, take an input, divide it into 3 parts, equal parts, and then retain a single one of them. One way of thinking of 1/3 that is more traditional is to actually say, well, we take one thing, something that represents 1, and then we retain only a third part of it. So this is 1/3. And in general, we can think of fractions being represented by the output when we insert 1. So 1 for us, for now, was just a single dot, and we didn't really speak of dividing up a dot. But if we can say this square here represents 1, and we have this picture that we can divide up the square like a cake, then of course it's quite obvious that this slice here represents a third, and we can actually produce other kinds of slicings. So with the picture that such a square represents 1, we can write down as squares and rectangles the representations of all the other numbers. So this of course is 1, but we also have 2, this here stands for 3, and so on. We can represent negative numbers by a shaded or black square, -1, -2, and so on. And now we can even talk about 1/2. This is the result of putting this square into the 1/2 machine. We can have a third. We can make multiples of these fractions. So, for example, this here would approximately represent -7/4. So we get a whole continuum of rectangles, each of which represents a number. And come to think of it, the height of the rectangles plays absolutely no role. We cut along the horizontal. So we can also imagine that just this width represents 1. And what we are doing here is building up a number line. So without all this decorum down here, we get quite naturally the number line. This is 0, 1, 2, 3, -1, -2, 1/2, a third, -3, -7/4, and so on. Because remember, we introduced these copying machines as machines in which we would put in dots, but really doesn't matter what kind of thing we put in here, as long as it is something that we can copy at will, and now new divide up at will. So it's a sort of a continuous quantity. So these two ways of representing numbers on paper are very interesting because you can switch back and forth between them. Think of a multiplication, for example. We've seen how to represent a multiplication in this representation with squares or dots. So we said inner product A times B. If we represent A by some row of squares and we represent B with some row of squares, then the whole product gets represented by an array that is A rows wide and B rows tall. So we stay in the representation of little squares. Here we say a single square is 1, and here as well we say a single square is 1. But what, for example, if we choose another representation, like the representation with lengths? So we could, for example, say, let A be given by this length, and let B be given by this length. Then, of course, obviously, the product A times B is represented by the rectangle with these lengths. Just as it was for squares, we can think of these as continuous quantities and make a square out of them. It is quite instructive to look at a concrete example with fractions. So, for example, say this is 5/2 and B is, say, 17/6. Because then A will be 1, 2.5, and B will be 1, 2, and then 5, 6. And really look at the areas of these little rectangles here and check that the total area corresponds in fact to the product of these fractions. So this is in the representation where A and B, the factors, are represented with lengths, and we represent the product with an area. But when we make sense of the product in the representation of areas, this is a bit strange, but a classic exercise in geometry to say how can we multiply two lengths. And of course, most intuitively, the product of two lengths is an area, as we've just seen, but what sense does it make to multiply two lengths to give another length? Unit-wise, this is absolutely impossible. But if we don't think of these as physical lengths, but lengths that just stand in for numbers, there's a nice little geometric construction that gives us the product of these numbers as a length. And if you're familiar with similarity, it's quite an easy construction. You just write down two number lines, put in a unit here, then actually let me make B red, because blue is for the unit. Now A is, say, here, and B is, say, here. Then the construction is to draw a line from 1 to B, and then draw a line from this intersection through A down to this number line. And then we get here the total length stands in for the product A times B. Because what is this? If 1 gets scaled up to B, then A gets scaled up to A times B. And then of course you can ask all kinds of other questions. For example, let's have A equal B, and then draw a line here, draw a line here. Can we make A such that this here, A times A, is 2? Geometrically, there's nothing that prevents us, because this product here varies continuously, but it's quite not an obvious question whether A can actually be represented as a fraction, be something that comes out of copying machine. You see that we are starting to transition from the image of copying machines to the classical image of a continuous quantity that actually is a real number, not just a rational number. This will be important because we are now talking about lengths and areas representing numbers, and we need this kind of flexibility of different representations of numbers, not just as copying machines, but as geometric objects, to make sense of, for example, a triple product or quadruple product as they can appear in fractional expressions. But before we go on to fractional expressions, let me get a little bit more philosophical, because we haven't talked about units here. And I said, if we think of these lengths as geometric lengths, it makes no sense that their product should also be a length. So there's some confusion about numbers and units here. So what's really going on? We've talked about numbers, but we've used lengths and areas and also dots on paper to represent numbers. And in order to have this representation work, we needed to say, for example, this thing represents 1. Or if we work with lengths, we have to set up the length that represents 1. We also have to set up an area that represents 1. But these are just doodles on paper. They are representations of numbers. If we think about units, for example, meters or square meters or something, this is a tool to use numbers to represent a physical quantity. So here on the right we have quantities, and they are represented by numbers by means of a unit. So here we have to specify a physical unit by, for example, making a piece of metal and say this is 1 meter. It doesn't have to be an actual physical object, it can also be a definition as is used now for example, the meter, which is defined by the speed of light. But we need some way of a physical representation of the unit. Then we can represent a quantity by a number. Now these quantities can be lengths, they can also be times or force or whatever. But the confusion typically comes in when we talk about lengths and areas as physical objects. So here we have lengths and areas that are physical. And of course, for physical lengths, the product of two physical lengths can only give an area. But here, these were just doodles. These were just doodles on paper, very important doodles, very fun. But here we can absolutely say two lengths, they each represent a number, the product is a number, we represent it with a length as well. So these units, so to speak, are not the same kind of unit as a physical unit. A physical unit really puts restrictions of what kinds of operations are possible, much more so than in doodle algebra.